Calculus, video 30, more on the chain rule. So before we get there, let's just kind of recap what we know so far. A few of the rules for derivatives that we know. We know that the derivative of a constant function is equal to 0. We know that the derivative of e to the x is e to the x. Power rule. We know that the derivative of a times x to the n is a times n times x to the n minus 1. And then the trig derivatives. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. The derivative of secant of x is secant of x tangent of x. The derivative of cosecant of x is negative cosecant of x cotangent of x. All of those we should know. We should have those memorized. We have to know the rules of derivatives for power rule, e to the x, constant, and all the trig functions. In addition, we have the product rule. If we have a function h of x, which is the product of two things multiplied, f of x and g of x, h prime of x is f prime of x g of x plus f of x g prime of x. Then we have the quotient rule. For h of x is equal to f of x divided by g of x. Excuse me. We have h prime of x is equal to f prime of x g of x minus f of x g prime of x divided by g of x squared, quotient rule. And finally, the one we just learned, the chain rule. For h of x is equal to f of g of x, we have h prime of x is equal to f prime of g of x times g prime of x. Or maybe, sometimes it's helpful to write this without the x's. You might think of that as like h prime is equal to f prime of g times g prime, right? Sometimes getting rid of the x's is helpful as for memorization tools. All right. Today we're looking at an alternative notation for the chain rule. So far we've been using the chain rule, thinking about it in terms of like f prime and g prime, but we have another notation for derivative, right? We have our dy dx notation for the derivative. And we said before that f prime of x is the same thing as dy dx. They both mean the derivative function. So how can we rewrite the chain rule using our dy dx notation? All right, so I'm going to set it up like this. Let's let h of x equal f of g of x. And then we know that h prime of x, by the chain rule, h prime of x is f prime of g of x times g prime of x. All right, that's the chain rule we've been working with. The first thing I want to think about is I'm going to let y, actually, let me back up. Let's let u equal g of x. And so instead of having our inside function be g of x, think about that as just the letter u, where u is some function of x, right? So think about this as u is a function of x, meaning that u is equal to something, 2x squared plus 5x, right? It is some function of x. That's what we mean by that. Okay, so we're going to let u equal g of x, just to try and simplify these letters here. And then let's let y equal h of x. No, let me go back. Let's let y equal f of u. I like that better. I know that's an unfortunate notation, f of u, but let's move on. It is the convention that we use here. Let's let y equal f of u. So what am I saying here? It's really the same idea, y being h of x. If I let g of x in u, g of x equal u is g of x is u, then what we have here is replacing the g of x right here, I'm replacing that with u. And so I have f of u. F of u. If u is g of x, right here I have f of u. If y is f of u, then y is h of x, right? Y is f of u, then y is equal to h of x. So h of y is like the big function here, right? It is f of the inside function u. Okay, think about this then. We would have the derivative of h of x. That would be like the derivative of y with respect to x is equal to, kind of mapping these two things together, f prime of g of x, right? F prime of u, right? You can think about this as f prime of u. But y is f of u. So f prime of u would be like the derivative of y with respect to u. It would be the derivative of y with respect to u times g prime of x. Well, g prime, g is u, g is u, so g prime would be like u prime. G prime would be like u prime. U prime, we could think about that, since that's a function of x, as the derivative of u with respect to x. In other words, the derivative of y with respect to x, the derivative, is equal to the derivative of y, the outside function, right, with respect to u, times the derivative of the inside function with respect to x. And that is the alternative notation for the chain rule. It means the same thing, the chain rule, kind of the alternative notation. For y equals f of u, we have the derivative of y with respect to x is the derivative of u, the outside function, the derivative of y, with the outside function, with respect to u, times the derivative of the inside function u with respect to x. And that is the alternative form of the chain rule. And I know it probably makes a little more sense the first way you learned it. And that's often what happens, is the first way you learned it tends to make more sense. You think about it in those terms. But as we move forward, right, as we get into harder and harder material, this idea with this alternative notation for the chain rule, we end up using it more and more. So this will come back for us the more we get into the depth of calculus. So we should know it. dy dx is equal to dy du times du dx. Okay. The only other part of this video I want to continue with is just to practice some more. The more you can do the chain rule, the better. So I picked out a few problems that give students trouble, and just want to try working through several of these. All right, let's try h of x is equal to the secant cubed of x. We'll start there. Again, when you think about this secant cubed, what I want you to picture is, or even write down, secant of x cubed. Right, outside function is something cubed, inside function secant of x. Pause the video, see if you can find the derivative. All right, we should be getting h prime of x is equal to, bring the 3 down. Leave the inside function, leave the g of x function, now to a power of 2, times the derivative of secant of x is secant of x tan x. And if I rewrite this, this is 3 secant squared of x times secant of x tangent of x, which is 3 secant cubed of x tangent of x. All right, let's go even harder. Let's go with h of x is equal to the sine of 6x squared times the cosine of 6x squared. Okay, so what we have here is a product rule. I am multiplying two functions, the sine function times the cosine function. You should be seeing product rule. This is my f function, this is my g function, right? That part is not a chain rule. The chain rule comes into play here. When I take the derivative of the sine of 6x squared, the sine acts like the outside function, the 6x squared acts like the inside function. So while doing the product rule, and I do f prime, I have to do the chain rule on sine of 6x squared. Similarly, while doing the product rule and I do g prime, I have to do the chain rule on the cosine of 6x squared. Okay, looks something like this. H prime of x. I know it should be f prime g plus f g prime. That is the product rule. So f prime. The derivative of sine is cosine of whatever this inside function is, 6x squared. But because it's not just x there, it's an entire function, I now have to multiply that by 12x. That's the chain rule right there. That is, for a composition of functions, that is f prime of g times g prime. That is our chain rule. But that, I know it's a kind of double notation here, all of that is just f prime. I still need to multiply it by the g function, which is cosine 6x squared. All right, so this is the g function. So f prime, then g of x, plus, leave the f function, leave the sine of 6x squared, multiply that by g prime. Well, what's the derivative of cosine? The derivative of cosine is negative sine of the thing I have, 6x squared. But I need to multiply that by the derivative of the inside, 12x. All right, so we're just leaving the f function, that's the sine of 6x squared. The negative sine, 6x squared times 12x, that is g prime, but it's g prime using the chain rule. So we get this, we have cosine of 6x squared times 12x times cosine of 6x squared. That sounds like 12x cosine squared of 6x squared. Then over here I have a negative sign, so minus sine of 6x squared times sine of 6x squared times 12x. So 12x sine squared of 6x squared, which you could factor out the 12x from 12x, leaving us with cosine squared of 6x squared. The 6x squared here is like the angle, right? Cosine of the angle here. Cosine squared of 6x squared minus sine squared of 6x squared, which would be a great answer. Perfect, 100%. We could also use the double angle formula for cosine to simplify this a little bit further. If you remember back from trig, the cosine of twice an angle has three formula, one of which is cosine squared of the angle minus sine squared of the angle. And that's exactly what we have here, where the a value is like 6x squared. So cosine squared of 6x squared minus sine squared of 6x squared is the same thing as the cosine of twice the angle, twice 6x squared. Using that, we could say this is 12x times the cosine of twice 6x squared would be 12x squared, and you end up with this 12x cosine 12x squared, using that double angle formula for cosine. Okay, very good. Let's try another that's also a little bit more complicated. How about, let's go back to the original one I had. Way back up here was secant cubed of x. Let's take that one, but make it a little bit harder. Let's say k of x is the secant cubed, not just of x now, but of, say, 4x squared. Okay, so here's what we're picturing this. We're thinking of this as the secant of 4x squared all all raised to the third power, right? It's that whole function cubed. Derivative. We'll take the 3, we'll bring it out front, right? That's power rule. Power rule. Take the 3, bring it out front of the inside to the power of 2. K prime of x. Bring the 3 down. Now we have secant of 4x squared, all raised to the power of 2. That's the power rule, that's our outside function. But now I need to multiply that by g prime, the derivative of the inside function. This is chain rule, right? I have f prime of g, I've written that. F prime of g is 3 times secant of 4x squared, times g prime. But what's the derivative of secant? It itself is a chain rule with the secant being the outside function and the 4x squared being the inside function. So what you're thinking of is the 4x squared here. You're thinking of blob, right? There's your blob. Blob. The derivative of secant is secant of the thing, tangent of the thing. So this is secant of blob, tangent of blob. But our blob happened to be 4x squared. But we're not done. Because when we took the derivative of the inside, the derivative of g, that's g prime, the derivative of secant is secant tangent, but the inside function, 4x squared, is not just x. So now we have to multiply that by the derivative of 4x squared, 8x. This is like a chain rule inside of a chain rule. And after all that, we get 3 secant squared of 4x squared, secant of 4x squared, tangent of 4x squared times 8x, which if I simplify this is 24x, secant to the third of 4x squared, because secant squared and secant, and then tangent of 4x squared. There you go. Chain rule inside of a chain rule. Okay, maybe one more. We'll call it good for these examples. How about, this one looks pretty good. Z of x is equal to the 4th root of 2x over 4x plus 5. Hopefully you'll recognize this as 2x over 4x plus 5 to the 1/4 power, right? 4th root is to the 1/4 power. So this is just your chain rule, all right? We'll just do the chain rule, but when we do the chain rule, the derivative of the inside is a quotient rule. So maybe z prime of x, bring the 1/4 down of the thing in the middle, of the inside function. To the power of, subtract 1 from 1/4, you get negative 3/4. So that is f prime of g. But now I need to multiply it by the derivative of the inside function, which happens to be a quotient. So we have the derivative of the top, 2, times the bottom, minus the top, 2x, times the derivative of the bottom, 4, divided by the denominator, 4x plus 5 squared. Let's first simplify the numerator of that fraction there, the g prime. That's 1/4, 2x over 4x plus 5 to the negative 3/4, times 8x plus 10, distributing the 2 to both of those, minus 8x over 4x plus 5 squared. This is nice because my 8x's cancel, and we get 1/4 2x over 4x plus 5 to the negative 3/4 times 10 over 4x plus 5 squared. Let's see. How much simplifying do we want to do? Maybe we just kind of leave it with our 10 and 4, right? 10 and 4 can both divide by 2, so I'll call that 5 and that 2 there. You could distribute this negative 3/4 exponent to the 2x and to the 4x plus 5, and then combine those. Maybe I do. I don't know if it's worth the trouble. Let's just call this 5/2, bringing this 5 just out front, times 2x over 4x plus 5 to the negative 3/4 times 1 over 4x plus 5 in parentheses there squared. And I think I'll just leave it like that. Okay, I know I said that was the last one, but give me one more. Give me one more to work through. How about, let's go r of x is equal to 3x squared times the tangent squared of 5x. All right, give it a go. See how you do. Okay, hopefully you tried it out. Let's try it here. When I look at this, I see a product rule. I see a function here, 3x squared. I see a function here, tangent squared of 5x. So product rule, but I'm going to think about it like this. I'm going to think about it as 3x squared times the tangent of 5x squared. So when I look at that tangent of 5x squared, I'm thinking chain rule. Because when I take the derivative of tangent of 5x squared within the process of the product rule, I'm going to bring the 2 down. Then it's going to be tangent of 5x to the first. Then I'll take the derivative of tangent, which is secant squared of 5x, then times the derivative of the inside function, the derivative of 5x, which would be just 5. All right, let's work through it. So if we consider the 3x squared to be like the f function, and the tangent of 5x being squared, the g function, the derivative of r prime of x, is f prime. The derivative of f, 3x squared, that derivative is 6x, and we're just going to leave the rest of it. Plus. So this is f prime g. Then we'll have f, leaving the 3x squared, times g prime. Here's the hard part. G prime. So take the derivative of tangent of 5x being squared. I'll bring the 2 down. Then it will be the tangent of 5x to the first power. Then I'm taking the times the derivative of the inside. The inside here is tangent 5x. The derivative of tangent is secant squared, still of 5x. Still of 5x. Secant squared there being the derivative of the inside function tangent. So it's tangent of 5x times the derivative of the inside function 5x. Its derivative is 5. All that multiplied together. I might have added an extra parentheses I didn't need there, so let's try that. Okay, so we have 6x tangent squared of 5x. Alright, so I'm multiplying here. I have a 5, I have a 2, that's 10, and a 3 out front, that sounds like 30. Alright, that's the 3, the 2, the 5. Then I have an x squared. Then I have a tangent of 5x to the first power. And then I have a secant squared of 5x. So I have a 6x tangent squared of 5x plus 30x squared tangent of 5x secant squared of 5x. Common factor here, if I could pull something out, I could pull a 6, an x, and a tangent of 5x. If I do that, I'll be left with tan 5x plus 5x secant squared of 5x. So something like that for my final answer.